Thanks, Peter, for the self-introduction. My name is Chu Wang, PhD candidate in Curtin University. Today, I want to discuss the application of the linked data for cross-domain constraint information sharing in liquefied natural gas construction. According to the Cambridge report 2014, the global demand forecast for LNG is 470 million tons per annum by 2030, which means the number of the existing LNG plants needs to be doubled. However, building this type of LNG plant is very challenging due to the large size and also the increased complexity. According to the Figure 1, you can find the project success rate in petroleum sector is the lowest one. I think this situation can be even worse in Australia. So the Table 1 lists the current LNG, greenfield LNG construction project in Australia. All of them suffered at least 1 year delay and multi-levels of cost overruns. The pool planning has been proven as an effective method to improve the project performance. Currently, there are 4 types of pool planning methods in the market: last planning system, work phase planning, and advanced work packaging. The right figure shows the general procedures of the last planning system. You can find the constraint management is one of the key processes to make work ready and also secure the construction workflow. So constraints in my research, I define as anything which prevents work packages being successfully executed in the field. In my last publication, I classified the constraints in LNG construction into 3 main categories: the engineering constraints, supply chain constraints, and also the site constraints. Effectively assessing this constraint information is critical to reduce the planning uncertainties. However, in current practice, this constraint information is still locked in isolated systems and use different vocabularies and schemas. So there is not an effective way for project participants to assess this source of information through single searches. This study aims to develop a semantic approach for improving the cross-domain constraint information by leveraging the linked data technology. This figure shows the overall system architecture. There are 4 layers. In the first layer, the existing legacy data will be converted into IDF format through the linked data wrappers. In the second layer, the separate IDF datasets shown in different colors will be interconnected with each other to create a global data cloud. And in the third layer, the linked data cloud can be searched and queried by using the linked data engines, and also new triples can be inferred. In the fourth layer, applications related to constraint management can be developed. So in a linked data wrapper, there are 2 main components: the domain ontologies and the mapping rules. So during the IDF transformation process, the domain ontologies are used as the source of vocabulary, and the mapping rules are utilized to make sure the converted IDF dataset is expressed in a structure and the target vocabulary. In terms of the domain ontologies, reuse of existing ontologies is highly recommended. So in this study, the ISO 15926 ontology was reused to describe the LNG plant product, such as the piping, the equipment, and instrumentation and relationships. So the ISO 15926 is similar as the IFC standard in building industry. And also two new ontologies were developed to transform the constraint data and the planning data respectively. So in my research, I use the the advanced work package planning method. So that's why I developed AWP ontology. So if you use the last planner system or the work phase planning, maybe you need to develop your own ontology. For the mapping rules, three types of rules I will develop. The first one is used to convert the join data to IDF. This slide shows an example of converting the PID joins into the IDF data, and also we can use some graph editors to visualize our converted IDF data and compare these two graphs to visually check the accuracy of the conversion process. The second one is used to convert the table data to IDF. As the figure in the middle shows a sample pattern, which is used to convert the three table data into IDF. The third one is used to convert the document metadata to IDF, because in some situation, the project participants they prefer to get access to the raw document. Yeah, so we use the Dublin call to as the vocabulary to transform the metadata. In terms of the data interconnection, we have two types. The first type is the data interconnection among IDF data sets. The merged ontology, as shown in this slide, plays key role to set the external IDF links among the multiple IDF data sets. So the red line shows is the equivalent, is one of the IDF external links, the equivalent class. The second one is the data interconnection between IDF triples and the documents. So when we convert the document metadata to IDF, we can store the IDF in the IDF triple store, and the users can query the triple store and get the metadata of the document, especially the URI, and then using the URI to call for the raw document. A pilot case study was conducted to demonstrate the capability of the proposed approach. The following four types of data source we use. So this figure shows the final linked data cloud in the IDF XML format. You can find the prefix of the three different types of ontology, and also the converted engineering join data, the work package data, and also the constraint. The first application aims to help the project participants to quickly find the constraint information. This figure shows an example of using Spark query for searching all the site constraints related to this specific installation package. So we stored our IDF data in this Sparkle endpoint, and then use this type of query. When you run, you can get the full site constraints. You can also narrow down the searching result by adding additional conditions. For example, if the users are asking for the site constraints with the status of unremoved, yeah, he can what he needs to do is add this sentence, and then to unremoved site constraint will be returned. If the users want to query all of the constraints related to this work package, including the engineering constraint, supply chain constraint, and also the site constraint, you can use this type of query. But however, no items will be returned because there are not the direct links within the raw linked data cloud. So some inference rules need to be developed. Yeah, this one shows an example of the rule of listing all the engineering constraints. So if the user finds a triple, the question mark has related engineering work package, question mark O, And also the question mark O has engineering items, question mark item. In addition, the question mark item has a number of members, so we can infer that the question mark S has the engineering constraint with the question mark member. So using the same grammar, we can develop another rule for listing all the supply chain constraints. So together with the constraint ontology, like the has engineering constraint is subclass of has constraint, we can use the same query sentence to get all the constraints related to this work package. You can find different types of constraints. I think the total number is 13. Okay. The application tool is used to visualize the constrained data cloud, especially for the searching result visualization. We set up a remote REST Spark endpoint in the Defi semantic web import plugin. Here, and then you can visualize. This is an example of the triple visualization related to this IWP. So you can find this is the site constraint directly direct relationships listed in the raw data cloud, and also you can find some information on this IWP itself, and also the related construction work package, procurement work package, and also the engineering work package. For the third application, the users can access the raw document and also some public reference data library. So the user can directly click the URI in the searching result, and we go to the raw document and also the public library to check the details of the definition of the typing acceleration joint. Okay, in summary, we developed a linked data enabled platform, which includes two newly developed ontologies, 3 types of IDF data transformation methods, and also 2 types of data interconnection methods. In addition, a pilot case study was conducted. It's very successful in interlinking constrained data and also in data searching, visualization, and inverse actual information. Okay, that's all. Thank you.
Thank you very much. Questions, please.